Okay, duplex mode. As you already know, the duplex mode determines that way in which a spectrum allocation is used for uplink and downlink transmission. 5G has been specified to support the FDD, TDD, STL, and SUL. Each operating band is associated with the single duplex mode. And however, there are some examples I showed in this table of multiple operating bands with different duplex mode targeting the same block of spectrum. Two examples are presented in this table. Operating band N50 and N75 target the same block of spectrum, but operating band N50 specified for TDD operation, while band N75 specified for the STL operation. A similar pattern exists for operating bands N51 and N76. This allows different operators to use the spectrum in different ways. Here about the duplex mode concept. These figures illustrate the general concept of each duplex mode. FDD requires the pair spectrum, while TDD, STL, and SUL use unpaired spectrum. FDD uses two separated RF carrier, one RF uplink and one RF for downlink. The transmit using one RF carrier uplink, while the base station transmit using the other RF carrier downlink. Supplemental downlink refer to an RF carrier which is only used for downlink transmission. In contrast, a supplemental uplink refers to an RF carrier which is only used for the uplink transmission. And the TDD uses the same RF carriers for both the uplink and downlink transmissions. The U and BTS cannot transmit simultaneously in the case of TDD because they share the same RF carriers. Let's see some difference between the TDD versus FDD. TDD is attractive for systems where the data transfer is highly asymmetric because the radio between the uplink and downlink transmission can be adjusted appropriately and the RF carrier remain fully utilized. 4G uses fixed uplink downlink timing for TDD. Like we can say the network is configured to use a specific uplink downlink software configuration, and once that configuration has been chosen, the timing of the uplink and downlink subframe is fixed. But in 5G, support dynamic uplink and downlink timing for TDD. This allows the base station to dynamically change symbols or a slot between the uplink and downlink according to the requirement. For example, the number of uplink symbols can be increased while the number of downlink symbols is decreased if the volume of uplink traffic increases relative to the volume of downlink traffic. 2D devices benefit from not requiring a duplexer. As you know, this helps to reduce the cost of devices. Duplexer is required by FDD devices to extract the uplink signal from the antenna for reception, yes, while at the same time inserting the downlink signal into the antenna or transmission. The duplexer tends to increase the receiver noise figure in the receiver direction and generate an additional loss in the transmission direction. FDD is attractive for systems where the requirement for uplink and downlink capacity is relatively symmetric. FDD can offer higher throughput because data transfer can be continuous in both directions. The capacity associated with the pair of FDD carriers is greater than the capacity associated with a single TDD carrier, but a greater quantity of spectrum is required, assuming the equal channel bandwidth maybe. FDD can be simpler to deploy in terms of synchronization requirements. In general, it's not necessary for neighboring FDD base station to be time synchronized, but TDD neighboring TDD base stations require the time synchronized to limit the level of interference between the uplink and downlink transmission. As we said before also about the operating band, we have two types of frequency range, which is defined in 3GPP. One is sub 6 gigahertz, and second was frequency range 2, which is known by millimeter wave or higher operating band, which we discuss about the concept of the higher operating band. In the frequency range 1, in the bandwidth, it will be support channel bandwidth from 5 to 100 MHz, and channel access method will be FDD, TDD, STL, and SUL. Regarding frequency range 2 or millimeter wave, the bandwidth F2 or support channel bandwidths from 50 to 400 MHz, and channel access type will be just supported the TD network. See, operating bands belonging to FR1 are shown in these two tables. These bands support FDD, TDD, STL, and SUL as we said before, yes? All bands are numerated using prefix N. Bands N1 to N76 are refarming bands which have already been specified for use by your 4G network. These existing 4G bands may be reformed for 5G. We can say 5G operating bands N1 corresponds to 4G operating bands N1, and etc. Operating bands N66 to N70 are FDD bands but have unequal uplink and downlink spectrum allocation. These bands have more downlink spectrum than the uplink spectrum. It's interesting. And the larger bands within FR1 are the new 5G TDD operating bands, which N77, N78, and 79. These bands have the potential to offer high throughput at relatively low operating frequency. Operating band N78 is a subset of operating N77. Some countries may allocate operating bands N78 if the full range of operating band N77 is not available in that country. And each operating band is specified to support a specific set of channel bandwidths. These channel bandwidths depend upon the subcarrier spacing. It will be depend of the subcarrier spacing. FR1 supports subcarrier spacing, as we said before, 15, 30, and 60 kHz. This table shows the set of channel bandwidth for each operating band and each subcarrier spacing, 15, 30, and 60 kHz. In case of 4G, there is a 1-to-1 mapping between base station channel bandwidths and UE channel bandwidths. For example, a 4G base station channel bandwidth of 20 MHz require all UEs to also support 20 MHz channel bandwidths. In case of 5G, the base station channel bandwidth can be greater than or equal to the UE channel bandwidths. For example, a 5G base station could support channel bandwidth of 100 MHz, while a UE could not support the channel bandwidth of 20 MHz. Yes? Okay, in this case, the base station would recognize the UE capability and allocate a resource block within our 10 MHz bandwidth. Different UE could use different 20 MHz sections of the base station channel. UE which support the 100 MHz channel bandwidth could be allocated resource blocks from any location with the base station channel. In some cases, uplink and downlink channel bandwidths are not equal. FDD operating band N66 and N70, as we said in previous page, support asymmetric uplink and downlink channel bandwidths. For example, operating band N66 supported a 20 MHz uplink channel combined with a 40 MHz downlink channel. Similarly, TDD operating band N50 supports asymmetric uplink and downlink channel bandwidths. In the case, a 60 MHz uplink channel can be used in combination with an 80 MHz downlink channel like this, and etc. Channel bandwidths belonging to frequency range 1 extended up to 50 MHz when using the 50 kHz subcarrier spacing, and up to 100 MHz when using the 30 or 60 kHz subcarrier spacing. The channel bandwidths associated with some operating bands are limited by the quantity of available spectrum. For example, operating band N51 has only 5 MHz of spectrum, so only support the 5 MHz channel bandwidth. This is the explanation of this bandwidth, and also supported by each operating band by using the subcarrier spacing concepts. FR2 also in channel bandwidths belonging to frequency range shows in these tables. These bands support time division duplex TDD. The bandwidths available from these operating bands are significantly greater than those available from frequency range 1. That's why we can use for the capacity solution where we can increase throughput. The channel bandwidth supported by each of these operating bands are presented in this table. In this case, channel bandwidths up to 400 MHz are supported when using the 120 kHz subcarrier spacing. And 3GPP specify the UE radio transmission and reception requirements for the standalone base station architecture using frequency range 1 within, I think, 38.101, like this. Here I put the subcarrier for the frequency range 1 and frequency range 2 as you can see. 240 kHz just used for transmission synchronization signal PBCH. And when you are decreasing your subcarrier, your cell range will increase, and vice versa. When you are using the more subcarrier spacing, you will have the lower latency. About the millimeter wave propagation. Millimeter wave spectrum corresponds to frequency which have wavelength between 1 millimeter and 1 centimeter and correspond to the frequency range between 30 GHz to 100 GHz. From perspective of 5G, the range of interest is 30 GHz to 100 GHz. The millimeter wave spectrum is particularly interested because it offers the potential for wide channel bandwidth, the potential for high throughput. But regarding millimeter wave, we need to be considered it will be in this operating band and this higher operating, we have some challenges like it will increase the free space propagation loss, oxygen absorption at 60 GHz, and also water absorption at 24 GHz, raindrop attenuation, foliage attenuation. If I want to talk about foliage attenuation, I should say foliage can lead to significant attenuation within a millimeter wave frequency range. The attenuation is generally depends upon the carrier frequency and the depth of foliage. You can see this equation where the frequency in megahertz and depth in the meters. The example, the frequency of 30 GHz and the depth of 10 meters leads to loss around 17.5 dB, which is very high. And another challenge is will increase the building penetration loss, lack of diffraction, increasing the scattering, and increasing the reflection from a smaller object, and finally increase the block of propagation path with the millimeter wave. So in this case, you will have small cells, noise limited, you will have the challenges for the indoor coverage, here challenging outdoor to indoor coverage also, and then you need to use some new concept like beamforming, which the beamforming the both base station and UE necessary to improve the link budget, and also the rapid or fast handle required when the propagation path is suddenly blocked, like by truck, for example. The beamforming concept will be discussed in the next presentation, as I said.